the number 1, that means it's on. So that means you would then add that spot to every other spot that's a 1, and that's how you can tell what number each thing is. So that's how you can read a binary number. Now, there's this concept called 2's complement, and that's very important in our computer because really what our computer can be doing is adding and subtracting numbers. And adding in binary is pretty easy, but in order to subtract, you now need to have negative numbers. So in 2's complement, there's a really easy way to read a negative number. If the leftmost bit, in our case, if the 8th bit is a 0, that means you're looking at a positive number. And if it's a 1, you're looking at a negative number. So the reason it's called 2's complement is because in order to successfully subtract, let's say you want to take the number 5 and subtract 3 from it, you would basically do 5 plus 3, but you want to subtract. So you would have to get the opposite of 3. You would have to get the inverse of it, the complement. And that wouldn't give you the number you want. So all you got to do to that 3 is now, after you inverse it, you add 1. And then now all your subtraction and addition, they'll work just fine. So last thing is logic gates. They're pretty easy to read and understand. So if you want to look at the AND gate, you have 2 inputs, the X and the Y. Now, the only way for your output to be a 1 is if both inputs are 1s. If they're not both 1s, your output will be 0. And then if you look at the OR gate, you have the X and the Y. And the only way for you to now get 0 is if both inputs are 0. Once you have a 1 in there, it's automatically going to be 1. So you can read these charts pretty easy. XOR is you only get 1s if they're both different. So if it's 0, 1, 1, 0, and not is different because now there isn't 2 inputs, there's only 1. And all it does is if the input is a 0, you get a 1, and if you put in a 1, you have a 0. So that's how you can read logic gates. Okay, so just as a general overview of the 8 major parts in our computer, you would start off with the clock. The clock is like the heart of the computer. Every time the heart does another bump, or every time you get a new tick in the clock, your program now will go to the next step. So your computer isn't going to do anything without a clock because it's not going to progress. So the clock is very important in this computer. Then you have the registers, number 2. There are 2 registers, I guess, that you would look at right now, register A, register B. And all these registers do is they're storing one number. They're storing one 8-bit number, and you can choose what to do with it. And you can know what number's in it based on which LED lights are on. If it's on, it's a 1. If it's off, it's a 0. So that's what the register is doing. Then there's the arithmetic logic unit, the ALU. The ALU is the calculator of the entire computer. If you want to add what's in both registers, it has to flow through the ALU. If you want to subtract, ALU. Any math, it has to go through the ALU. Then there's the random access memory, the RAM. This is the main storage of the entire computer. You hold everything in here. Most importantly, you're holding your instructions. So you need to look at the RAM to know what to do at step 1, step 2, step 3. Without your instructions, obviously nothing's going to actually happen. Then number 5 is the program counter. This will display whatever step you're up to. So right now, if you look at it, you can see that it's number 2. That means you're doing whatever your second step is. So whatever you program it to be. Then there is the output, or the output register. This is just like any other register, like A and B, except instead of displaying whatever your number is in binary, it's now displaying it in decimal on your display. So you can see the number 42. That means the number 42 is being held in that register. Number 7 is the bus. This is very important because this is how all your information travels. If you want to get information from register A to display on the output register, it has to travel through the bus. So all your information is traveling through the bus. It's like one really long highway, whatever you want, it'll go through. Lastly, like one of the most important, if not the most important parts of the computer, is the CPU control logic. What this does is it makes sure everything happens. It if whatever your instruction is to do, it makes sure it gets executed and it does everything you need. So if you want A and B to add, it'll make sure A and B adds. So that's the general overview of the computer. And yeah.
So I'm going to explain the clock module. So the clock of the computer moves you through the commands the computer is going to make one step at a time. Our clock can be controlled manually or automatically, and we also have a switch that can turn it off altogether. When it's being controlled automatically, we have something called the potentiometer, which can change the pace it's blinking at without having to replace resistors and change those out every few minutes. And then when it's getting controlled manually, we control it with a button. And the switch in the middle switches between automatic and manual. So here is a video of the clock working, and on the left is a diagram of the so as Elior explained, the computer takes ones and zeros through different gates, and so these are the gates that are working in the clock module.
So I'm now going to explain the next component of the computer, which Elior briefly touched upon. So now that we have our clock functioning, we're able to kind of move through a process of the computer, as Maya described. But we want to be able to store data, of course. So this is where the registers come in. We have our A, B, and our instruction registers. So the registers for our computer are only 8-bit registers. Now that's incredibly small. To put that into context, that means that we could have really only 2 to the 8th possible values stored. So if we're working only with positive numbers, we would be able to store from 0 to 255. That would give us 256 total possible values, which of course is 2 to the 8th. But as Elior briefly described earlier, we have our 2's complement. So that would enable us to get from negative 127 to positive 128 with 0 inclusive. And that would give us our 256 total storage. Now, the registers, they're able to store these values. They're able to store these binary values. And the way that we built the circuitry, if you could see on the bottom, you see that red LED. So when in the larger register schematic, there are 8 LEDs for each register, representing whether that individual bit is on or off. And then, of course, the total 8 make up a binary number. And in this case, from negative 127 to positive 128, including 0. And then the registers are able to store the value and then communicate with the bus, which is what Elior described as well. So as the user of the computer, we're able to see at all times what value is currently stored in the register based on the LED lights, the red LED lights. And really the way it works is from an electrical perspective, is whether there's voltage going through, as Elior described earlier as well. So if there is voltage going through a bit, for example, then it would be brighting up, and we would have a red light. And if it was off, it wouldn't be on. And then, of course, we could begin to compute through our ALU, and that's when the registers begin feeding in to the ALU and then communicating with the bus.
Next we have the RAM, the random access memory. And what the random access memory does, the RAM, is it stores the program the computer is executing as well as any data the program needs. Now, on a larger computer system, you would usually have both RAM and ROM. RAM, random access memory, ROM, read-only memory. Read-only memory holds more permanent instructions for the computer. But because we have such a small computer, we only have 16 bytes of RAM. we cannot do that much with it. It limits the complexity of the programs that we can run. Next, we have the ALU, which has been sort of briefly referenced, and it is capable of performing various bitwise and arithmetic function operations on just binary numbers. In this case, ours is only able to add and subtract. In larger ones and more complicated ones, it can obviously do multiplication, division, and so forth. So on the top and the bottom, we have the A and B registers in their larger form that Maurice described. And then in the middle, we have our ALU, and on the left, that is going to the bus. Now, in the ALU, we have a chip called an LS245, which allows us to choose when we want to send data to the bus. So we can store, based on voltage that we are putting in, we can tell the registers in the ALU whether to send information to the bus. We saw a manual version of this, so to speak, in the clock with the switch. When it is on the monostable mode, when we're only using the button, the individual timers for the automatic are still running. They are just not sending a final output to the clock output. And just as another quick review of binary addition, you have 2 to the n minus 1 being your places, and then you add them by 1, 2, 4, 8, and so forth. And next we have Adam.
All right, code. And if it's not, if else, you'd want to skip to another set of instructions. And that action of skipping is executed by the program counter, because the line value of where you want to jump is then inputted into the program counter. And then I'll just briefly mention the chips that are used. This is actually relatively simple. We have just a program counter chip, and then the tri-state buffer, which is that output that enables it to be submitted to the bus. Now I'll move to the output and output register. I'll focus more on how the output mechanism works rather than the register itself. But just briefly, the register is very similar to the one Maurice, the 3 other registers in the computer, as Maurice explained. And the output, however, is very unique. And how you can envision it, as you can see on the slide, is it's basically the equivalent of the screen you're viewing this video on. Instead of having to determine what the number equivalent of the bit values are within either the registers on the bus, wherever, you can easily just be able to check your code, check if everything's working properly by looking at the number itself and not having to do the calculations. This is accomplished through the output, and it's just a series of these 7-segment displays that you see in the bottom right-hand corner of the slide. And just generally, it can be extremely difficult to kind of program the 3 of these using simple logic gates. And it would probably end up adding 5 to 7 more breadboards to the actual computer, because the truth table, or the outputs desired to display a certain number, are so complex that it's much more efficient to use something called an EEPROM. An EEPROM is just a basic way of being able to almost memorize the truth table, or the desired output values when an input address is put into the EEPROM. So for example, how it works is you just basically tell the EEPROM, I want the value of, I want to display the number 8, and it'll then output the desired binary value that will then put 8 on these 7-segment displays. So this is just generally what the output register and output itself looks like on the breadboard computer. You can see the EEPROM is that larger chip in the middle between the display as well as 3 other chips on the side. And just generally, in order to how we get 3 digits to display with one EEPROM, you may be wondering, if the EEPROM can only output 8 bits at once, how do we do all these displays at the same time? And that actually happens through a series of multiplexers, which basically says I want to output to this to that digit, or the next digit. And what happens is that actually occurs in very rapid succession. So while it's actually for the number, for example, 123, it's really going 1, 2, 3, 1, 2, 3, but it's going so fast that it appears to be 123. Now, just lastly, I wanted to touch on the control logic, which obviously, as Elior mentioned, was the most important part of the computer. And it's basically the conductor of the orchestra. It allows all of the individual modules to work synchronously and properly, and it actually interprets the instruction that's located in the RAM whose location is designated by the program counter. And it interprets that to say, for example, I want to add the numbers 46 and 37. It'll go into the ALU, and then I want to put that ALU output on the bus, and then I want to store that in the RAM. And that entire action is executed through this control logic, basically controlling the outputs and inputs, mainly of those two LS245s that we've referenced a few times before. So this concludes our presentation. Now, if anyone has any questions, you can feel free to ask, comments. And I hope that initial picture we showed you guys a few slides ago is easier to understand, and now you can see what each individual breadboard is actually able to accomplish and how it all fits in together to enable us to perform more complex tasks.
All right. So as Adam indicated, we're opening it up to questions, but I just want it to be known that one of the questions I want to ask at some point is to hear from each of the students what they found most interesting or what they learned that surprised them the most in this project. But I can wait until we've heard any other questions that parents, teachers, or administrators have about the project.
So I have a question. And I am like so lost on computers, and Dr. Stordetta has been great trying to teach me about how they work. But Maurice, in your presentation, you were talking about how the calculation could only go up to 255. Does that mean, like, I know it sounds ridiculous, but if I needed it to go to 320, it couldn't do it? Like the number 320 wouldn't work? It only calculates to 255?
Yes. So kind of to respond to your question, Adam, maybe you want to go back to that slide, if possible. So we also, in the short answer is really yes. It does not go up to 350. I mean, that's really the limitations of this computer. And a bit of the longer answer is that there's something known as the carry bit. So yes, in some sense, you can do computation that is higher than 255, but it won't be represented as that number. So let's say we get up to the number 300. You'll have all of the bits, the 8 bits that are possibly added up to the 300 would be included, but then those following bits that would make up the rest of the 300 would not be there because there simply isn't enough representation to show that there is 300 because we only have 8.
Got it. Okay. Okay. Very interesting. Yeah.
I'm just going to add. Oh, go ahead. I'm sorry. I just want to add a little bit of relating this to the computers that we as people in the year 2021 use. Sort of the minimum thing that you would recognize as a computer would be a so-called 16-bit computer. Now, you may initially think, well, gee, if it was only twice as hard to make a 16-bit as an 8-bit, why didn't you guys just go for the 16-bit? But in fact, the amount of space that would have taken up to go from an 8-bit to a 16-bit is realistically, it's going to be about 8 times as large. And today's computers, modern computers, are actually almost exclusively the ones that you interact with on your desktop or an iPad or an Android phone. Those are 64-bit computers typically. And so the complexity of those is so astronomically larger that it would be it would take all of the size of this school to build a 64-bit computer. And we were tempted to do that, but we were worried about where to put particularly the younger children while we were building it. And so that's why we exercised some restraint there. If there are other questions, I'd love to hear that. Otherwise, I want to ask each of the students in a turn of presentation what they found most interesting about this. Other questions from those that are not the presenters? Happy to take them at this time. All right, well then let's go over to the sequence in which students spoke. I believe it started with Elior, and then Maya, and then Maurice, and then Alex, and then Adam. So maybe Elior, you can talk about just maybe 1 or 2 thoughts about what you weren't expecting or what you found most interesting.
So something that I really did find crazy was when you're building the computer and you see him build the first display, the output, you see him, as Adam said, make like an entire breadboard in half to make one number show. And then in order to get 3 of that, there's so much space that it's taking. It's crazy. And then he pulls out something called an EEPROM, and all of a sudden then 5 to 7 extra breadboards is just stored into one tiny chip. And it's just crazy how that's possible. And yeah, that blew me away.
So I thought it was really interesting to see how small each gate was. We did everyone some coding in machine language beforehand for each of the gates, and you would expect them to be so much larger with how much thought and code had to go into each of them. And so I did work specifically with the AND gate and the OR gate for my module. And I was just so amazed for that first module at how small they were.
So I mean, I focused mainly on the registers, and I mean it's just mind-boggling to see how this large computer that we're building, this 8-bit computer, is eventually then condensed into a little tiny chip that goes into our phone. And not only is that little tiny chip not an 8-bit, it's actually a 64-bit, as Dr. Stornetta alluded to. So it's just incredible to see how much storage we're able to contain nowadays. But then also to kind of get into the nitty-gritty of it and the circuitry and building the computer itself was definitely an incredible experience.
As somebody who works primarily with software, it's fascinating to me what happens when you can't see exactly what is going on. When with software you have errors that are that give specific error messages so you can see exactly what went wrong, or you can see like exactly what's going on at all times. But for the hardware, there's so much inside these tiny little chips that we can't see, and so it blows my mind that before 64-bit computers, before 32-bit computers, when people were still working with 8-bit computers, the amount of skill and knowledge that was necessary to advance just using those sort of just floors me.
So the most interesting thing for me was definitely it's kind of on the same topic as everyone else, but the fact that I'm having issues obviously like everyone else in this class, finding the correct wire to fix as Ethan mentioned, finding where the error is and seeing which connection is correct. I mean the fact that 64-bit chip is on such a magnitude. Like I can't even begin to fathom how how it's able to work with almost like when you buy a laptop in the store, it works out of the box. And the kind of how there's zero errors, all these there's billions of transistors in there, and they're all working almost perfectly and synchronously. And experiencing the errors myself, it kind of brought things into perspective, and I'm almost in awe. Of like the hundreds of thousands, millions of calculations going on in our codes without a single error most of the time. And that's something I found incredible. And just one last thing, we just want to thank Dr. Stornetta for this incredible opportunity, and for making, for bringing this project and also this class in general for us. Because as people are passionate about computer science, it's almost an unrivaled opportunity to be able to hear from someone from the industry himself. And I know Maurice is echoing my appreciation. I'm sure everyone else shares my opinion. And we are grateful for Dr. Stornetta's contributions to the school and to our computer science program.
Yeah, I mean, sort of like I had a couple weeks ago, I was talking to Maurice about this. I think it was a couple weeks ago, may have been only a week ago. But sort of we got so incredibly lucky with you, Doctor. Like to be able to have such an impressive and accomplished teacher for a course that had never been taught before. This wasn't like, oh, we need a better teacher for this, oh, we need a better teacher for that. Sort of, and Mr. Berger, this is a testament to the school as well. Sort of finding Dr. Stornetta is sort of changed this year, like so much for the better. Like this year would not have been the way it is without him. So thank you, and thank you, Dr. Stornetta.
It's a great title for a book. Finding Dr. Stornetta. I like it.
Okay, well, obviously the reason I'm wearing my mask is because I'm blushing. But again, I hope parents feel good about what it is their students were able to accomplish. The answers are not in the back of the book in this class. And it's a great way for them to get a glimpse of what it's like working on actual problems post-graduation. So I appreciate everyone that's been able to make it out today. A recording of this video, as I indicated, is going to be available at the RKYHS tech website. And we hope to see you again for our